Welcome to DAR Tutors for Online and Home Tuition. Today, we will delve into electron pair sharing reactions, a fundamental concept in IB chemistry higher level. This topic, R3.4 in your syllabus, covers how chemical species form new bonds by donating or accepting electron pairs. By the end of this video, you will be able to, first, define and identify nucleophiles and electrophiles. Second, describe the mechanism of nucleophilic substitution. Third, describe and explain the mechanism of electrophilic addition. Fourth, apply Lewis acid-base theory to reactions, including coordination compounds. And finally, calculate the oxidation state of metal ions in complex ions. Let's begin by defining our key players, nucleophiles and electrophiles. Understanding them is crucial for all organic reaction mechanisms. A nucleophile is an electron-rich species that has a lone pair of electrons available to donate and form a new bond. We can say it is nucleus-loving. An electrophile is an electron-deficient species that has an empty orbital available to accept a pair of electrons and form a new bond. It is electron-loving. In any reaction involving these two, the nucleophile attacks the electrophile. This movement of an electron pair is represented by a full-headed curly arrow. So, we draw an arrow starting from the electron-rich nucleophile and pointing towards the electron-deficient electrophile, showing the electrons moving. Nucleophiles are generally of three types. The most common are lone pair nucleophiles, which donate electrons from a non-bonding pair. Examples include water, hydroxide ions, and halides like chloride. Next are pi-bond nucleophiles, which use the electrons from a pi bond, such as in alkenes or arenes. The high electron density of these double bonds makes them reactive. And less common, sigma-bond nucleophiles, like the borohydride ion, where the electrons come from a sigma bond. This type of nucleophile is used in reduction reactions. Electrophiles can be either neutral or positively charged. They all have an empty orbital to accept electrons. Examples include carbocations, halogenoalkanes with their partially positive carbon, and species like aluminum chloride. A useful way to think about electrophiles is that they often contain a site with a partial positive charge, delta plus. For instance, in a carbonyl group C=O, the highly electronegative oxygen pulls electron density away from the carbon, leaving the carbon with a partial positive charge. This makes the carbonyl carbon an electrophilic center, readily attacked by nucleophiles. Therefore, identifying the nucleophilic and electrophilic centers in molecules is the first step to predicting how they will react. Nucleophilic substitution reactions involve one chemical group replacing another. A nucleophilic substitution reaction involves a nucleophile replacing a leaving group on an electrophile. Heterolytic fission is the splitting of a covalent bond where the more electronegative atom takes both electrons. For example, when chloromethane breaks apart, it forms a methylcation and a chloride anion. Let's consider an example with hydroxide and iodomethane. The reaction is hydroxide ion plus iodomethane produces methanol and iodide. Hydroxide is the nucleophile. Iodomethane is the electrophile. Iodide is the leaving group. Let's look at the step-by-step mechanism. Step 1. The nucleophile attacks the electrophile. Step 2. The leaving group departs. The products are methanol and iodide. This is how nucleophilic substitution reactions proceed. Let's work through another example. This type of question is common in IB exams. We need to complete the equation for the nucleophilic substitution reaction between sodium thiophenolate, an ionic compound, and chloromethylbenzene. The best approach is to first identify the nucleophile, the electrophile, and the leaving group. Sodium thiophenolate is an ionic compound. It dissociates into a sodium cation, Na+, and a thiophenolate anion, C6H5S. This anion has lone pairs on the sulfur and a negative charge, making it our nucleophile. Chloromethylbenzene is an organochlorine compound. The polar carbon-chlorine bond creates a partial positive charge on the carbon atom bonded to the chlorine. This makes chloromethylbenzene the electrophile. And as in our previous example, in a reaction where chlorine leaves the carbon, a chloride ion, Cl, will be the leaving group. Now we can draw the mechanism using curly arrows. We draw an arrow from a lone pair on the sulfur atom of the thiophenolate ion to the carbon atom bonded to the chlorine atom in chloromethylbenzene. Simultaneously, a second arrow is drawn from the CCl bond to the chlorine atom. This results in the formation of a new CS bond and the departure of the chloride ion. The product is a thioether. Notice how the negative charge on the thiophenolate ion is transferred to the chloride ion. We've seen how nucleophiles attack electrophilic centers. Now let's explore a different reaction type: electrophilic addition to alkenes. Unlike alkanes, alkenes are unsaturated hydrocarbons because they contain a carbon-carbon double bond. This double bond is made of two parts, a strong sigma bond and a weaker pi bond. The pi bond is formed by the sideways overlap of p orbitals, creating a region of high electron density above and below the plane of the sigma bond. This pi bond is weaker and more accessible to other reagents, making the alkene itself act as a pi bond nucleophile. So, in an electrophilic addition reaction, an electrophile attacks the electron-rich pi bond, and the double bond breaks to form two new single sigma bonds. A classic example is the reaction of ethene with bromine. Although bromine is a nonpolar molecule, its electron cloud can be polarized as it approaches the electron-rich pi bond of the ethene. This creates a temporary dipole, making one bromine atom partially positive. The pi electrons of ethene attack this partially positive bromine atom, forming a new carbon-bromine sigma bond and breaking the bromine-bromine bond. The other bromine atom becomes a bromide ion. This process forms a cyclic bromonium ion intermediate, a three-membered ring with a positive charge on bromine. A bromide ion is now available. The bromide ion, acting as a nucleophile, attacks one of the carbons in the bromonium ion from the opposite side of the ring. The CBr bond from the ring breaks, forming 1012-dibromoethane. This product has two bromine atoms, one attached to each of the original carbons of the double bond. Let's explore other electrophilic addition reactions with alkenes. These are key for organic synthesis. First, the addition of hydrogen halides. Hydrogen halides like HCl, HBr, and HI add across a double bond to form a halogenoalkane. The mechanism is similar to the bromine example. The pi bond of the alkene attacks the partially positive hydrogen of the hydrogen halide, forming a carbocation. The halide ion then attacks the carbocation. Now, for unsymmetrical alkenes, where the two carbons of the double bond are bonded to different groups, there's a rule that determines the major product. This is Markovnikov's rule. It states that when an unsymmetrical alkene reacts with a hydrogen halide, the hydrogen atom of the halide will bond to the carbon of the double bond that already has the greater number of hydrogen atoms. The halide will bond to the carbon with fewer hydrogens. Let's apply this to propene. The double bond is between carbon 1 and carbon 2. Carbon 1 has two hydrogens, while carbon 2 has only one. Following Markovnikov's rule, the hydrogen from HBr will bond to carbon 1, and the bromine will bond to carbon 2. This gives us 2-bromopropane as the major product. Next, let's look at the addition of water, also known as hydration. Water itself is not a strong enough electrophile, so this reaction requires a strong acid catalyst, like concentrated sulfuric acid. The acid protonates the water to form H3O+, the hydronium ion, which acts as the electrophile. The pi bond attacks the H3O+, forming a carbocation. The water molecule then acts as a nucleophile, attacking the carbocation to form a protonated alcohol. Finally, another water molecule deprotonates the product, regenerating the H3O+ catalyst and forming the final alcohol. This reaction also follows Markovnikov's rule for unsymmetrical alkenes, resulting in the formation of the more substituted alcohol. Let's look at why Markovnikov's rule works. The answer is rooted in the stability of carbocation intermediates. To understand this, we need to consider the stability of carbocation intermediates. Let's look at the addition of hydrogen bromide to propene. Here is the reaction. When the pi bond reacts with a proton from HBe, it can lead to the formation of two possible carbocations. The first is this: a primary carbocation. The other possibility is a secondary carbocation. The secondary carbocation is more stable than the primary carbocation. This is because the alkyl groups attached to the positively charged carbon are electron donating. They push electron density towards the electron-deficient carbon, helping to spread out and stabilize the positive charge. This effect is called hyperconjugation and inductive effect. Here's an order of carbocation stability. Tertiary is most stable, then secondary, then primary, and methyl is least stable. So in this reaction, the pi bond attacks a proton from hydrogen bromide. This can give either a secondary carbocation or a primary one. The secondary pathway leads to the major product. So Markovnikov's rule is really a consequence of the thermodynamic stability of carbocation intermediates. The reaction pathway with the lower activation energy leads to the more stable carbocation and gives the major product. Understanding this principle is crucial for predicting the outcome of many addition reactions involving unsymmetrical alkenes. Lewis acid-base theory. The Bronsted-Lowry theory defines acids as proton donors and bases as proton acceptors. The Lewis theory provides a broader definition based on electron pairs. Importantly, this definition links directly to nucleophiles and electrophiles as we have discussed. Electrophiles are electron pair acceptors, so they are Lewis acids. Nucleophiles are electron pair donors, so they are Lewis bases. Let's consider an example that is both a Bronsted-Lowry and a Lewis acid-base reaction. The formation of the hydronium ion. Here, water donates a pair of electrons to the hydrogen ion to form a coordinate covalent bond. Water is a Lewis base, and H+ is a Lewis acid. In Bronsted-Lowry terms, water is a base because it accepts a proton, and H+ is an acid because it donates itself as a proton. However, the Lewis definition is broader and can explain reactions that Bronsted-Lowry theory cannot. Let's look at the reaction between boron trifluoride and ammonia. Boron trifluoride, Bf3, has only 6 electrons around the boron atom, making it electron deficient. It is therefore a strong Lewis acid, or electrophile. Ammonia, NH3, has a lone pair on the nitrogen atom, making it a Lewis base, or nucleophile. The ammonia donates its lone pair to the empty p orbital on the boron. This forms a new coordinate covalent bond. The resulting compound is called an adduct. Notice there is no proton transfer here, so this cannot be described by Bronsted-Lowry theory. This shows the power of the Lewis definition. The Lewis acid-base concept is also central to understanding coordination chemistry, which is the study of complex ions. A complex ion consists of a central transition metal cation, which acts as a Lewis acid, bonded to several other molecules or ions, called ligands, which act as Lewis bases. The ligands donate a pair of electrons to the transition metal cation, forming coordinate covalent bonds. For example, in the hexafluorosilicate ion, open bracket SiF6 close bracket 2-, silicon tetrafluoride SiF4 acts as the Lewis acid, and the fluoride ions F- act as Lewis bases. The fluoride ions donate lone pairs to the silicon atom. This forms a new complex ion. Each bond between silicon and fluorine is a coordinate covalent bond, even though they are indistinguishable from other covalent bonds once formed. Another important concept is coordination number. In the hexaquantical 2 ion, open bracket Ni left parenthesis H2O, right parenthesis 6, close bracket 2+, there are 6 water molecules bonded to the central nickel ion. The coordination number is 6. Some ligands, called multidentate ligands, can bond to the metal ion at more than one point. For example, 1,2-diaminoethane has 2 nitrogen atoms, both of which can donate electron pairs to a metal ion, forming 2 coordinate bonds from a single ligand. Finally, complex ions can exist as part of neutral ionic compounds, called coordination compounds, with counter ions. In hexaaminic cobalt 3 chloride open bracket CO left parenthesis NH3 right parenthesis 6 close bracket Cl3, the complex ion, open bracket CO left parenthesis NH3 right parenthesis 6 close bracket 3+ is the cation, and 3 chloride anions, Cl- are the counter ions. Let's learn how to find the oxidation state of the central metal. We'll focus on this example. Calculate the oxidation state of iron and potassium 3 iron, cyanide 4, hydroxide 2. Step 1. Let's find the charge of the counter ions. The potassium ions, each with a charge of +1, give a total charge of +3. Step 2. That means the charge of the complex ion must be -3 to balance the charges. Step 3. Next, let's examine the ligands. Both cyanide and hydroxide have a charge of -1 each. Step 4. We need the total charge from all the ligands. 4 cyanides and 2 hydroxides give us 4 times -1 plus 2 times -1, which equals -6. Step 5. Now set up your equation. The oxidation state of iron plus the total ligand charge equals the charge of the complex ion. Step 6. Now solve for X. The oxidation state of the metal plus -6 equals -3. So X equals -3 plus 6, which is +3. So the oxidation state of iron is +3. Let's work through another oxidation state calculation. These problems test your ability to recall ligand charges. This time, we will calculate the oxidation state of the metal ion in CrCl2NH342SO4. First, we determine the charge of the complex ion. The sulfate ion, SO42, has a 2-dir charge. Because 2 complex ions are needed to balance 1 sulfate. Each complex ion, CrCl2NH34, must have a charge of +1 to maintain neutrality, so the complex is CrCl2NH34+. Next, we identify the ligands and their charges. We have 2 chloride ligands, Cl-alkene, and 4 ammonia ligands, NH3. Ammonia is a neutral ligand, so it contributes a 0 charge. Now we calculate the total charge from the ligands. 2 chloride ligands give 2 times 1, which is 2. 4 ammonia ligands give 4 times 0, which is 0. The total charge from all ligands is 2. Finally, we set up our equation. The metal charge, X, plus the total ligand charge, 2, equals the overall complex ion charge, +1. Solving for X, we get an oxidation state of +3 for the chromium ion. This is a chromium Th3 complex. You should now be able to distinguish between electron-rich nucleophiles, which are Lewis bases, and electron-deficient electrophiles, which are Lewis acids. We then saw how these species interact in 2 key reaction types, nucleophilic substitution and electrophilic addition. For electrophilic addition, we explained why alkenes are reactive due to their high pi electron density, and why Markovnikov's rule is followed for unsymmetrical alkenes based on carbocation stability. We also expanded our acid-base knowledge with Lewis theory, seeing how nucleophiles are Lewis bases and electrophiles are Lewis acids. This led to our discussion of coordination compounds, where we practiced calculating the oxidation state of the central metal ion. These concepts form the bedrock of much of the organic and inorganic chemistry you will encounter. A solid understanding here is essential for your IB exams. Take some time to review these topics. For expert tuition and personalized support in IB, A-Level, and IGCSE chemistry, we invite you to contact DAR Tutors. Our experienced educators can help you master these complex topics and achieve your academic goals. Let's put your knowledge to the test with some IB-style practice questions. I encourage you to pause the video, try to solve them on your own, and then resume to see the worked solutions. Here is question 1. Take a moment to consider the definition of a nucleophile and a Lewis base. The correct answer is B, H2O. Both nucleophiles and Lewis bases donate electron pairs to form new bonds. Water has 2 lone pairs on its oxygen atom, making it an electron pair donor. Let's analyze the other options. CH3+ is a carbocation, which is an electrophile and a Lewis acid, an electron pair acceptor. CCl4 is a stable, nonpolar molecule with no lone pairs available for donation, so it's neither. CL3 is an electron-deficient compound, a Lewis acid, and an electrophile. Here is question 2, focusing on reaction mechanisms. Pause here and determine if this reaction is nucleophilic substitution or electrophilic addition. Recall what we learned about the reactivity of alkenes. The correct answer is electrophilic addition. Alkenes with their electron-rich double bond are pi-bond nucleophiles. They are primarily attacked by electrophiles, such as bromine in this case. The reaction results in the addition of atoms across the double bond, which breaks. This is the hallmark of an electrophilic addition reaction. Question 3 requires you to apply Markovnikov's rule to an unsymmetrical alkene. Think about which carbon in the double bond has more hydrogen atoms and what that implies for the addition of HB. Let's draw 2-methylpropene. The double bond is between carbon 1, which has 2 hydrogens, and carbon 2, which has no hydrogens attached to it. According to Markovnikov's rule, the hydrogen from HBr will add to the carbon with more hydrogens, which is carbon 1. Adding hydrogen to carbon 1 forms a tertiary carbocation on carbon 2, which is the most stable type of carbocation. The bromine then attacks this stable tertiary carbocation to form 2-bromo, 2-methylpropane. Therefore, option B is the correct answer. Question 4 tests your understanding of Lewis acids and bases. Identify the electron pair donor and the electron pair acceptor in this acid-base reaction. Let's analyze the species. AlCl3 is aluminum chloride. The aluminum atom has only 6 electrons in its valence shell, making it an electron-deficient species with an empty orbital. This means it is an electron pair acceptor, which is the definition of a Lewis acid. The chloride ion, Cl, has 4 lone pairs of electrons, so it is an electron pair donor, a Lewis base. The reaction shows chloride donating a lone pair to aluminum, forming a new coordinate covalent bond and creating the tetrachloro aluminate anion, AlCl4. Our final question requires you to calculate the oxidation state of a central metal ion in a coordination compound. Use the strategy we discussed. Determine the charge of the complex ion, the charges of the ligands, and then solve for the metal's oxidation state. First, the charge of the complex ion is given as +2. Next, we consider the ligands. Water, H2O, is a neutral ligand. It carries no charge. Now we can set up our equation. Let X be the oxidation state of copper. The charge of the copper ion plus the total charge of the ligands equals the overall charge of the complex ion. So, X plus 4 times 0 equals +2. Solving this, X equals +2. Therefore, the oxidation state of the copper is +2. This is a copper-2 complex. This concludes our comprehensive look at electron pair-sharing reactions and related HL chemistry topics. We've covered nucleophiles and electrophiles, mechanisms for nucleophilic substitution and electrophilic addition, Lewis acid-base theory, and the chemistry of complex ions. I hope these explanations and worked examples have clarified these concepts for you. Practice is key to mastering these topics for your IB exams. If you require further assistance or personalized tutoring, please do not hesitate to contact our tutors. Our experts are ready to help you succeed in IB, A-Level, and IGCSE chemistry. Thank you for watching.